We are talking about probability in mathematics. So, what is probability? Means, if I toss it, okay, so, okay, so if I toss a coin, then what is the probability that it will be head? So, in probability, there are two things. One is sample space, how many samples we are creating, and in the sample space, how many we want. Okay, sometimes it is called that solution is hidden in the problem. If we are able to analyze the problem neatly, minutely, intricately, solution is hidden in that. Okay, so no need to look at other places for the solution. Many times solutions are hidden in the problem itself. So, what is the probability that if I am tossing a coin, then it is head? Okay, now how means what is the sample space we are talking? So, the sample space is head and tail. I am not saying either head or tail. Head is one sample, tail is one sample. Now, out of these, how many I want? I want only one. So, 1 by 2. If I toss it 3 times, 1 time, 2 times, 3 times, okay, what is the probability that I get head, head and head? Okay, if we see the books, then there are lots and lots of formulas are there, like dependence, independence, and then factorial, and then then it comes to like a matrix false positive or false negative, and then sensitivity and specificity, and so many things. Okay, so if I am tossing a coin 3 times, then what is the what is the probability that I'll get head, head and head in 3 times? Okay, what is the sample space? How many sample space we are generating? So one sample space is head, head, head. Another is head, head and tail. Another is head, tail and head. Another is head, tail and tail. Another is head, tail and head. Then another is head, tail and tail. Another is tail, head, head, tail, head, tail. Tail, tail, head, tail, tail, tail. Okay, so there are 8 sample spaces. Now I say it is mutually exclusive and this and that, and then it is 2 to the power 3 and something like that. But okay, so if I am tossing 3 coins, it is equivalent to I have, okay, so I have 3 coins in my hand. I think I can show it. So there are 3 coins in my hand, and if I toss it, then what is the probability that it is head, head and head? Same thing. If I toss a coin 3 times, or I have 3 coins in my hand and I toss, okay, then what is the probability that it will be head, head and head? So probability is what is kind of how many sample space we are generating, and out of those sample space, how many we are picking. So we are generating 8 sample spaces. If we are generating 8 sample spaces, 1 we are head, head and head. So that is 1 by 8. So getting the probability of head, head and head is 1 by 8. If I toss it 2 times, then we are generating four kind of sample space. In sample space, four items are there. One I want. Now mutually exclusive and this and that. If I toss this coin, then if head comes, then only I toss this coin. Then if this comes, then formula. You just sit back and think in your sample space how many items you are getting. Okay, generate the sample space, and once you are done with generating the sample space, then now decide which one you want, how many you want, so which all you want, and count by whatever items in count. So solution is hidden in the problem. If I have a clear problem space, if I understand the problems in probability, the biggest thing is that people do not understand the problem. What is the problem? If problem is identified, then getting to the number of items in the sample, or if problem is identified, then getting item in the sample, then picking the items what we want. So solution is hidden in the problem itself. Okay, so now a little bit kind of more hazy, overcast problems, like I believe this is a known problem and people they know it. So like at a place or in a city, in a town, at a place, so car kind of there are taxi and they kind of they are deployed, they serve people. And 15% of the taxi is blue and 75% of the taxi is red, or it is not blue. 15% are blue and 75% are not blue. It may be red, it may be green or yellow. So many things. Now, in a kind of, there is a hit and run case, and it's a dark, and then one person is kind of his eyewitness, and now he is saying that the hit and run case, that taxi is blue. So there are 15% taxi in city, those are blue, and in hit and run case, he found that the taxi is blue. This is one case. Now let's see simple case. There are 15% taxi in city are blue. In a hit and run case, what is the probability that the taxi is blue? This is one question. In a hit and run case, what is the probability taxi is blue? So every 100 taxi, 15 is blue. So the probability that in a hit and run case the taxi is blue is 15 by 100. So it is 15%. 0.15 is the probability that. Now another question. Now a person is saying that he saw that taxi is blue. So we proceed on the question. Now that Mr. Judge, he is not very happy with his reply. Means it is a dark night, there are few light here and there. So it is a high chance that he may kind of identify it wrong. So it was tested. In the same kind of scenario, environment was generated, and it was found that 80% of the time he finds the correct color in that scenario. If car is red, then he is saying it is red. 80%. 20% scenario, he is saying something different. Now, what is the guarantee? Now, what is the probability he is saying truth? Probability has little bit degree, but there is no different kind of probability. So this falls in a kind of bias theorem, conditional probability. All probability are conditional probability. So bias theorem, like it talks if there are two events and they are orthogonal, they are not related. If angle between two, if I draw in vector diagram, an angle between two events is 90 degree, it is considered as orthogonal and they are not related. Otherwise they are related. Okay, to some degree they are related. That we have seen in our tutorial that the essence, like we saw the dot product and cross product. So essence will be there if we talk about if we talk about any angle, if it is not orthogonal. So if two events are orthogonal, then based upon the occurrence of one event, what is the probability that other event has occurred? Okay, if they are really orthogonal, then there is no probability. I mean, there is intersection. Little bit intersection is there. And then we try to find, means angle is not absolutely 90 degree. Okay, it tends to 90 degree. Okay, we will see many examples. Now we stick to this example. So 15% car are blue and person is identifying it is blue, but 80% of the case only he is identifying anything that is correct. Now, what is the probability that car, the taxi in hit and run case is blue? If I see the Bayes theorem, then in Bayes theorem, I say PA by B. If B has occurred, then what is the probability of A occurring? Conditionally B has occurred. Okay, so I say probability, all probabilities are conditional probability. Okay, if I am tossing the coin, I will not talk about the Europe and America. Okay, so I talk only about the coin only. So conditional is the coin, tossing of the coin. So there is nothing that is unconditional. Okay, but anyway, so it's good that there is a bias there. Okay, now can we create a sample space? Now we have 15% car as blue, and out of that, now he is identifying 80% as correct. What is the guarantee that he is talking true? Okay, now we come to as if car is identified as blue. Okay, this is sample space. Like if I am tossing 3 times, what is guarantee, what is probability that it is head? If that person is identifying a car, how many cars are blue, that is not the question. If a person is identifying a car as blue, then what is the probability that it is true? It is blue. So in Bayes theorem it will come as probability of blue by person identifying blue. Now, if I see blue cars, then 80% are only blue. So 20% are gone because he is not identifying it. Okay, so out of 100 car, 15 into 0.8. So that much car is only blue from that person's eye. And out of 85 cars, 20% cars are blue. Okay, so means this is what he is doing. So now 85% 85 into 0.2 and 15 into 0.8. That many cars he is saying it is. Out of which, how many cars are actually blue? 0.15 into 0.8. Okay, so in our sample space, we are not talking about out of blue what is the probability. How many cars are identified as blue? So in blue, there is a percentage of cars that is identified as blue, and in rest or in red, this much cars has been identified as blue. So the sample space item contains that many cars. Now in that many cars, we have to pick which one is actually blue. So 20% of the car in blue, actually it is not in the sample space at all. They are out. If they are not in the sample space, there is no meaning of finding solution inside that sample space. Okay, so probability is only one. You have to find the sample space, items in sample space, and pick the item what you want, and then just divide. Okay, 10% of people in the world, they talk English. 10% of the people. I mean, this is hypothetical data. Okay, I am saying, I don't know what is the actual truth. Okay, 1% of world's population lives in Egypt. Hypothetical data. Okay, whatever how now in the Egypt's population, 1% people they talk in English, means they are bilingual. They talk in Egyptian and they talk in English. If a person, okay, speaks English, what is the probability that he is from Egypt? This is biased. Now, condition is now there are two orthogonal, means as per the Mr. Bias. So one orthogonal, one vector is people in the world they are speaking English, and one orthogonal vector is people in the world who are living in Egypt, means they are totally unrelated. People are speaking English and people living in Egypt, they are totally unrelated. Okay, but there is intersection. That's why there is a probability, otherwise there is no probability. Now, if someone is speaking English, then what is the probability that he is from Egypt? Okay, now, if I am saying the condition, so now if I expand my sample space, so person is speaking English, so now it is simple example. It is simpler than car example, taxi. Now we find that how many people there they talk English. So 10% of the people they talk English. And now we will pick what we want. Okay. So 10% of the world they talk English. Okay. And 1% of the world they are from Egypt. Certainly there is intersection. Okay. Certainly there is. What we are talking is, what is the strength of the intersection by people who are talking English? So, in our sample space, all people who are talking English, they comes, and now inside that we will pick who are from Egypt. Okay. So if 10% people talk in English, then it is 10. Okay. One greatness about Bayes' theorem is actual amount is not required. Means we can work in percentages. Okay. But again, it is a subset of probability one. And probability is only one. Means you have to find a sample item. So I won't say that this way of probability you have to find like this and this way. So probability is found in only one. Okay. Now, if I know the sample space, inside that I have to pick how many people they belong to Egypt and they speak English. So 1% of the people they belong to Egypt. Inside that 1%. So it will come around 0.01%. So 0.01 by 10. So that is the probability. Okay. So probability is finding the sample space, items in sample space, and then picking up the item. There is a place where 10% of the people are corona positive at that moment. Hypothetical data. Okay. So there is a place that 10% of the people they have corona infection. Now, if a person goes to hospital to get tested that he has corona, okay, now 70% of the chance that he will be tested corona if he has corona. So kind of true positive. So if he has tested corona and actually he has corona. So if a person has a corona, 70% of the chance of the test success means success of chance of the success is means out of 100 corona patients, 70 corona patients are tested that they have corona, and 30% they are said you don't have corona. False. Okay. If a person he does not have corona and he goes for test, 90% of the chance is there that he will be tested negative, true negative, and 10% 10% chance is that he will be tested corona. So out of 100 people they are free from corona and they go for test, and 90% will be said that okay you don't have corona, so you are kind of no need to be annoyed, and 10% will be given label as corona. A person is going for test and he is tested corona. What is the probability that he has corona? Okay, now we'll go for bias theorem and then mutual exclusive and then PA by B and then some sigma, okay, and then some pi and so many calculations. Not like that. Okay. Now think from the person. Now we have to generate that items in the sample space. We are saying a person is tested corona. What is guarantee that he actually has corona? How many people are being tested corona? That is the sample. That is difficult to find in probability. If you catch the sample space, if you catch the problem, then you have to just pick the solution. That's it. So, how many people are tested corona? Now I have 10%, I have 90%. 90% people they do not have corona. 10% people they have corona. If these people go for testing, then 90% would, then 70% would be accepted as corona. So out of this 30% are rejected from the sample space at all. So only 70% are coming in the sample space. Out of 90%, 10% people are tested corona, even though they do not have. So 10% from the 90%, they are coming in sample space, and out of 10%, 70%. So here, out of 90%, the people who do not have corona, 10% are entering into the sample space of the corona. Out of 10% of the people who actually have corona, 70% people are entering into the sample space. Now, I have a sample space. Inside that sample space, how many people now he has actually, so how many people have actually have the corona? How many people actually have the corona by how many people are inside the sample space as corona, as per all the environment. Okay, so that would come around 10% of total people have corona. So 10% into 0.7 by 10% into 0.7 plus 90% into 0.1. So if a person is going for test and if he has been detected corona, then this much is the chance that he actually has the corona. So can we see the sample space, how it varies depending upon the kind of probability that all the events, corona and not corona, these are two events. All the events in the sample space, how they are being identified, correct? Means as per the bias theorem, there can be many theorems, not only bias theorem. There can be infinite theorems. So infinite scenarios will be there. This is one scenario. So we'll see that funny things that how probability we generate. But this is the core of mathematical probability. Just understand the problem, solution is just stay waiting point. So that way. Okay, so a further discussion on probabilities will proceed. Probability is not very difficult. It comes under kind of a simple topic, But if it is not understood, then it can be very difficult. Okay, so probability is about understanding problem space. So, what is probability means what is the chance of something to happen. So, a deep understanding of the problem space is required. As much time as possible should be given to understand the problem space. Creating sample space. So, once problem is understood nicely, then sample space of items should be created, picking required item and calculating the division. Okay, so how we understand the problem space and then how we create the items in sample space and how we pick the items. So 99% of the work is here, or probably 100% of the work is here, and then these are minor. Okay, understand problem domain. So go in deep and try to give. Okay, so like if the problem is in kind of iterative or recursive, okay, in a meta way, that is the better English. So if it is in a meta way, then go in the kind of inner frames and till you hit the kind of the scene that, okay, so this is the problem. Think about the main actor in the problem. There can be many actors in the problem. Okay, one actor will carry the key. So that is the guy who will create the who will make you understand the problem space. So problem space need to be give as much time as possible and go in depth of the problem. Okay, then decide for the actor or guy who is the problem, and that can explain this idea in detail. Then we can think about the solution. Okay, create sample space of items. So based upon the actor, whatever the actor we have selected, now we go with many items. Items can be orthogonal. So later we will see in Bayes' theorem. Okay, items may not be orthogonal. So like we can see there are many items, not actor. Many items are there and they may be intersecting each other at some point. So if there are 4 items, okay, these 4 items, they make the complete problem domain or complete sample. If I add all 4, then it is equal to 1. So if I add all 4, it is equal to 1. Okay, so idea is if I add all 4, then adding all 4 should become 1. Okay, so that is the idea. Now create sample space of the item. So inside that, this green, whatever green we are seeing, here we are interested in. Okay, these are the full items that are in the problem domain, and then all the greens what we see, here we are interested in. Okay, not everywhere. This is crucial. So in problem space, only green color we are interested in. Once we know it, then we have to pick the places what we are looking for against what we are interested. What we see in the black background, that we are not interested at all. So what is the probability where we are interested in, and then total green. So since I have colored these two as orange, so I have made green plus orange. Otherwise we can say total green. So total green is the denominator and orange color is numerator. So this is what we are looking for among all green. What we see not selected, not colored, we are not interested in. So that is the probability. If we understand this much, okay, first understand the problem, find the guy who is the problem, and then, so this is full domain where all items exist, and we are interested in these many regions, and inside that we are picking these two. If we are picking these two, then whatever we are picking by whatever we have opted for, that we have to divide. Non-colored region we are not interested in. Okay, so now the question is, a coin is tossed 3 times. Okay, so a coin is tossed 3 times. What is the probability of getting head, head, and head? A coin is tossed 3 times. So as per the discussion, we can kind of think like there are 3 coins as we have discussed. Okay, so it is as good as there are 3 coins. I can say like this. Okay, so there are 3 coins. It is as good as saying like this. There are 3 coins. Okay, and who is the actor? Actor is a triple coin, means 3 coins. That is the actor. Okay, now we create the sample space of items. So we have 8 items. A coin is flipped 3 times, but it is creating, as per the actor, it is creating 8 items. These are items, and items we can see head, 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 tail, like that. And it is as good as these 3 coins are tossed in various combinations. Okay, so what will happen if I compute a kind of, if these 3 coins, they are tossed in various combination, so what would be the result? Okay, so that can be thought of. Now, select the item. Okay, what you want? You want this. Out of all combinations, you want this. So, if there was question like what is the probability of getting head, 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 and tail, head, and tail? Okay, this is the question. Head, 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 and head. So, now we have 2. This and tail, head, and tail. These 2. Okay. In that scenario, it will be 2 by 8. Now, here we are question is only head, head, and head. So, it is 1 by 8. Okay. Now, I have another question. A bag contains 2 blue ball, 3 green ball and 2 red balls. Okay, so the way it is drawn, I believe it is opposite way, so I'll change it. Okay, so a bag contains 3 red balls, and 2 green balls. Okay, so this is pretty straightforward question. A bag contains 2 blue ball, 3 red ball and 2 green balls. At a random 2 balls are picked. What is probability that picked balls are not blue? Who is the actor? Dual ball. We are picking 2 balls. Okay, so 2 balls are actors. If they are the actors, now we have many items. And in each item we have 2 balls. Ball 1, ball 2, blue 1, blue 2, blue 1 R1, blue 1 R2, blue 1 R3, blue 2 R1, blue 2 R2, like that. Okay, so in every pick it becoming one item, and each item is like this. Where we are interested in? We are interested in all the items where blue is not coming. If that is true, then there are 10 items where blue are not coming, and there are total 21 items. So the division if we make at the end, then it will come as 10 by 21. Okay, so no one has guts to draw this one and then find this one. So if 2 balls, blue ball, 3 red ball and 2 green ball are there. So blue, red and green, then we have to find combination of 2. So we select any 2 at any time where 2 can be shuffled, like 1 blue and 1 blue. Blue 1 and blue 2 are same as blue 1 and blue 2 are same as blue 2 and blue 1. So it will not be permutation, it will be combination. Okay. So whatever we are selecting, their intermixing is not required. So if I say blue 1 and red 1, and if I say red 1 and blue 1, so both are same. So we will use combination. So blue, red and green, whatever they are in the count, combination 2. So every time 2 are selected. So if I do that, it will become 21. Now, what we want, red and green combination 2 where blue is not there. So it will come as 10. So 10 by 20. Okay. So, but in mind, this is not a bad idea to think about the sample space. Okay. Whenever we go for probability, we find the actor, we think about the sample space. Once we think about the sample space, then we think about what we are going to pick up, and then how we create the sample space. Then we can think about the permutation and combination. Okay, so that is the scenario how we calculate the probability. So at the end, so like here, whatever the combinations are happening, we are taking all the combinations in the example, and then we are picking whatever we want and we are dividing. But in conditional probability, means probability can be of multiple grade, complex also. There we will see that this diagram has importance. Right now we are selecting everything, and then we are picking the item, and then we are dividing it. So that is the scenario. we saw a few aspects in calculating probability and it was interesting. Means we start from analyzing the problem domain and then in depth we did the analysis. So if you are doing analysis of a problem and it is taking time, then you are lucky. Means analyzing problem is the most crucial thing in calculating the probability. Once problem is analyzed nicely, then you are picking the active. So whatever we see as problem, probably it is kind of only superficial, surfacial. Okay. When you go in depth and you look into the kind of problem descriptions and what is required, then you think about the actor. Now, when you think about the actor, then you think about the kind of sample space. So in sample space, what are the items would be filled? Once sample space is kind of finalized, then you pick items from the sample space and that is what you want. I mean, whatever you want, that you pick from the sample space. Analyze the problem, look for the actor, create the sample space of the items, and what you want, just pick here and there, divided by your sample space of the item. So, sample space, whatever you have the scenario, I would say problem space or the scenario. So, sample space would not be the kind of same thing, so it would differ. Like we saw in examples, like if I have 3 balls, that is kind of a problem or that is a scenario. Okay, but from actor's perspective, 2 balls are required. Okay, that changes the sample space completely. Okay, where two balls are placed. If actor is at one time 3 balls are picked, sample space change. Doesn't matter what is the scenario that 2 balls are red and 3 balls are green and 2 are blue, whatsoever. Doesn't matter. So what matters is what is the decisive factor, what we want. Okay. So like if I am kind of flipping or tossing a coin, then coin, I am tossing 2, coin is only 1 in my hand and I am tossing it 2 times, 3 times, 4 times. So that is the crucial. That decides what would be the sample space and how items would look. Then we just think about how many or what are those items that we need to pick. Okay. So now we will proceed on kind of bias theorem. So bias theorem comes as important when we kind of think about 2 orthogonal items, not 1 item, 2 orthogonal items. Okay. So that is bias theorem. Like as we kind of described that there are people who talk English in the world, and if I say that there are people who talk English in the world, and then kind of the intersection of the Egyptian people and English people, means people who talk Egyptian and English, so those are kind of 1% of the world. So that is not what we are. So we are looking at 2 kind of items that are orthogonal. 10% of people talk English in the world and 1% of the people, they are, means all these data are fictitious, just to kind of demonstrate the bias theorem. So 10% people talk English in the world and 1% of the people in the world are Egyptian. So they are completely unrelated. So 2 unrelated items now comes into the picture. And if I know each one's probability and the probability of any one against other, like if I say that I know what is the probability that if I know that if people are talking in English, then he is a English speaking Egyptian. Okay, so condition is that if a person is talking English, so that is the condition. Then he is English speaking Egyptian. Or orthogonal can be, we gave example like there are two cars in at a place or at a city, and one is blue and one is green, and now in accident the person who witnessed the accident, he said it is blue, but he can identify true only 80% of the time. Then, like if I talk about if 15% cars are blue and 85% cars are red, and there was accident, then what is the chance that a blue taxi made the accident? So that is 15 by 100. But now, so this is kind of a normal scenario. But in kind of little advanced scenario, now either a person saw the taxi who made the kind of a hit and run case accident, or we can just place a scenario that in that life the probability of the chance of finding the correct taxi is only 80%. What is the act? Now, what is the condition what is the probability that blue car made the accident? 15% cars are blue. And if someone is kind of a witness, he witnessing the blue car made the accident or hit and run, then what is the probability that actually blue car it is involved in hit and run case? Okay. So first, who is there? Okay. So actor is the eyewitness, means because if it is 80%, then analysis, whatever sample space we are making, that will change. If it is making 90%, if it is making 50%, 40%, irrespective of exact amount of blue car and red car, things are varying as per the actor. Okay, so that kind of dynamic situation in probability. So that we'll see. So we'll see Bayes theorem, and Bayes theorem is important in kind of machine learning area, where NLP like natural language processing. So there Bayes theorem is important. Like if I have to find like a document belongs to which category, like if I have a book and I can kind of parse the words or sentences, then I should be able to say that this book is it belongs to some literature or some kind of a thriller. Okay, so this kind of thing we can guess. So that is again probability, and it belongs to here. Okay, so that we'll see in future NLP when we see the machine learning. So now we'll see the Bayes theorem. Okay, so we'll proceed on Bayes theorem. So that is the idea. Okay, so we'll include the slides for the Bayes theorem. Okay, so now if we see the scenario we presented, like if this is the case where we have items, then if we create the sample space of the items, then we may not select everything, and we select whatever is matching to the scenario, and then we pick whatever is required and we calculate the probability. So this leads to kind of a Bayes theorem. Okay. So what is Bayes theorem? Like if there are two items A and there is another item B. Now if I say if A is the condition, then what is the probability? So can we see the coloring? So B is kind of this color, okay, so reddish color, and this is white color. So now we can say that how much is reddish inside A. So if A is the condition, if A is the full world, okay, in this world A and B both are there. So if I calculate the probability of A and B, probably it would be 1. But if A is the world, okay, so that's why we say everything is condition. Okay, so if condition is bigger, then inside that A and B exist. And if condition is A itself, okay, then what is BA? So what we are trying to say? Okay, if bigger is the condition, then we can say that, okay, A and B are comprised in kind of in bigger condition. Okay, probably I can save it. Okay, now in bigger condition A and B, they exist. Okay, so in bigger condition A and B exist, and inside A there is a portion where B exists, and inside B there is a portion where A exists. So how we can kind of nomenclature give this portion? If I know A, if A is the condition, then what is the probability B inside A? If this is the condition, this full rectangle is the condition, then what is the probability of A and what is probability of B? If A is the condition, A is the big master, A is everything, A is 1, then what is the condition of B, probability of B being in A? Or if B is the master, B is everything, then what is condition of A and B? Okay, so suppose I know PA, probability of A, probability of B, so these are in global picture, and probability of B inside A. If A has happened, then what is probability of B? Considering B as a full world. If I consider full world is a real world, then what is probability of A and probability of B? If A being the full world, then what is probability of B inside A? If I know these, then what is probability of A inside B? This is orthogonal. This is what we are talking. So this can be considered as orthogonal case. Okay, and it is a kind of big thing. So being these two events, I would rather say, being these two events as orthogonal. Orthogonal means 90 degrees. Okay, so now these two are orthogonal in the sense now if I know PA, PB and A, B inside A, then what is A inside B? So, I mean, whatever we have discussed by now, so it is same thing in different discourse. So that whatever we see, same thing. But Mr. Bias is Mr. Bias. So in different discourse. So we know PA, we know PB, and if we know PBA, provided A has happened, and B, then what is the probability of BA? Okay. So this is the scenario. Now, if I see PA, okay, what is PAB? If B has happened, then what is probability of A inside B? Then it is probability of B, and then it is the PAB. So PAB is nothing but P intersection B by PB. So if I know P has happened, B has happened, what is probability of A inside that? Probability of B and their intersection. So this is what we know. Now, okay, so this is a general formula. Now we'll talk about this. So same deal, whatever we have drawn, now same thing. Now intersection is clear. So this full white, whatever inside white is A, and whatever inside red is B, and whatever the intersection is from A's perspective, it is BA. From B's perspective, it is AB, and both are different. PBA and PABs are not same. So it is proportion as related to B. So B may be very big. Okay, and it is a proportion related to A. Okay, so if B is very big, then PAB would be small, and A is small, then PBA would be big. So these two are not same. They depend upon the size of B and A. Now we'll see the same formula. PA by PAB equal to PAB intersection by PB. Same as PBA and conditional PBA intersection. So if it is intersection, both are same. Now if both are same, then both sides we can equate, and then we can say that PAB equal to PB, PA, PBA and PA. Okay, so mathematics formula is formula. What is significance of the formula in the real world? So that is the idea, but we understood. So if I want to know probability of A in B's condition and probability of B in A condition, their intersection, and probability of B and probability of O divided by. This is what we saw. Means this is common sense also. And if I equate, then probability of A if B has happened conditional, and probability of B A has happened conditional. So it would be same as these two intersections are same, intersection AB and BA, and then probability of A provided B has happened is probability of B separately and probability of A, and then inside AB. Okay, so this is the formula. We can draw as a tree also. Okay, that we'll see. So this is the bias theorem. How it lies in our concept of actor and sample space and selected item and division. This is what we have seen. Okay, so we'll add slides. These are local slides. Okay, so Mr. Bias theorem. Now, okay, so what is the question now? 15% blue and 85% red taxi in a city or at a place. Hit and run case in night. So someone hit and run. Eyewitness find taxi as blue. Eyewitness can make 80% of true assessment in night condition. Okay, if this is the scenario, then probability being eyewitness being true. Probability of eyewitness being true. Okay, so probability of Okay. Now probability of eyewitness being true. Okay, so if this is the scenario, okay, now can we see the blue taxi? Means the way we are drawing the items. Okay. Now can we see the blue taxi? So who is the actor now? If this is the case, then who is deciding the fact? Eyewitness. Eyewitness is the actor. How? Eyewitness is the actor. Okay. Now, as per the eyewitness, now the reality is gone. The way we are keep on saying here. Okay. So, like green color is whatever is the reality from someone's eye. Someone's eye. Okay. So, these are gone. These non-colored are gone. Only this comes into the picture. Okay. And inside that we have to find what is we want. Now, from blue text, now from eyewitness perspective, 80% of the cases eyewitness can find true, otherwise 20% is false. Now, if blue taxi is coming in front of eyewitness, all blue taxi, okay, 80% of it he finds correct. And this area, that is 20%, he is saying it is red or not blue. Now, red taxi is being brought, all red taxi is being brought near to him. I mean, whatever the sample is. And few he is identifying as blue. And rest he is identifying as red. I mean, he is identifying a big part as red, but few he is identifying as not red. So from, okay, so if I say, okay, or from this diagram, if I see the white color kind of circle or ellipse, white color circle and red color circle. So full white color circle is actual blue taxi and full red color is actual red taxi. But Mr. Eyewitness, part of it he is saying it is blue taxi, rest he is just discarding. Okay, so those scenarios are not coming into the picture at all. But in red taxi, few taxi he is identifying as blue, and I mean it's not red, and rest he is identifying as red. So anyway, red taxi we are not interested in. And here, even it is blue, but it is gone out of the scene. Now, as per the eyewitness, if I say eyewitness is true or not, now number of blue car, okay, I mean probability of the blue car. So if I say a number of the blue car, how many blue car that eyewitness is finding? Blue car in blue car. Okay, so how many blue car and blue car in red car? Red taxi. So blue car in blue and blue car in red. Now, what is the probability? Blue car in blue by blue car in blue plus blue. So, total blue he is finding. Okay, total blue is this region, and this region. So, this region is not into the computation. This region anyway it is not into the computation. So, total number of blue car that fellow is finding is, okay, some blue car in the blue and blue car in the red. So total blue car is blue car in the blue and blue car in the red. Then this is the kind of sample space. This is a sample item. And inside that we are picking this. Okay. So, now we are interested in this. Okay, so we are interested in this, whereas our sample space is this much and this much. Okay, so that is the calculation. So this is the actual basic probability, how basic probability works, the way we demonstrated. So this is the basic probability. Now Mr. Bayes probability. Okay, so same question. Now the white circle, what we are saying is PA, and there is another circle called PW. PW is witness. So red car gone. This is Bayes' theorem. So there are two circles now. One is the blue car, and one is the Mr. witness car. Okay. Now if that is true, then PA and PW, two entity. And if we know the A, then what is the probability of W inside A? And if we now what we want that provided Mr. Witness cars, Mr. Witness is saying identifying these many cars, inside that how many are blue? So PA by witness means if witness is the condition, then what is the probability of blue? So can we see it is different? Okay, so if we know that this is Mr. Witness car, all green color, and this is the blue car, so if the white color is the blue car, then that is PA, and if this is Mr. Witness car, that is PW. And if I know inside blue car, if it is a condition is blue car, then what is the condition of Mr. Witness finding the blue car inside the blue car? And if all witness, as per the witness, whatever the blue car is inside that, what is the true blue car? So PA by W, we are trying to find where we know PA, we know PW, and PW by A. So this is Bayes' theorem. Okay. Now, if I see the PW, that is nothing but PA into PW by A. Okay. So it is PA and PW by A and PB in the sense we keep on talking PA and PB. PA and PB. So in this way, PB, and W by B. So PA is blue and PB is red. So if I draw a tree, then A is blue and this is not A. So if I see that 0.15 is PA, where 0.85 is red. Now inside blue, 0.15 into 0.8 is the blue that is witness is finding, and this he is discarding. Now inside red, this much witness is finding as blue, and this he is discarding. So now as per the formula, so it is PAW by A, PBW by B, and then it is above is the actual blue car. So that would be lead to 0.15 into 0.8, 0.15, 0.8, 0.85. So this is Bayes' theorem. Bayes' theorem brings probability in different world. Okay, where now if I talk about the orthogonal, keep on talking about orthogonal. So if I talk about orthogonal, okay, so now the actual orthogonal is Mr. Witness, means I would say like this, the blue car and another is Mr. Witness. So these two are orthogonal. Can someone believe this? Okay, now I have another example. Okay, example by example. Now there is a corona, 10% corona at a place, at a town, in a city, 10% corona, 90% corona free. This is the actual case. Now corona test confirms 70% of the corona positive in corona cases. Now if a corona patient is going for corona test, 70% chance as it will come as positive. Whereas a corona free case goes for test, 90% chance that it will come as free, corona negative. Okay, it is true negative. I would say it is true negative and it is true positive in machine learning technology. Okay, these are new things to kind of to deviate people. But anyways, now a person has been tested corona. Probability that he is corona case. Okay, he is a corona case. Probability that he is a corona case. Person has been tested corona. A person goes for test and he was tested corona. What is a guarantee probability that he is actually a corona patient? Okay, now 70% of the corona tests are positive. So if he is a corona case, then high chance, but let's see the scenario. Now there are two circles. White circle is corona positive case and red circle is corona negative case. It means people are corona free. They don't have corona. Who is the actor as per? Okay. Now I have to really change. Okay. So who is the actor? So actor is corona test. Actor means hero. Hero means who changes the movie. Okay. So corona test. Okay. Corona test changes the movie. Whatever corona test result comes in, corona test is the hero. Okay, like earlier, eyewitness was the hero. If he is identifying 80%, scenario is different. If he is identifying 20%, if he is identifying 90%, scenario is different. Here, corona test is the hero. If corona test is 70%, confirm 70%, 90%, scenario is different. If it confirms 50% and 80%, scenario is different. So corona test is the hero. Now, among the corona positive cases, actual positive is this one, and these are coming as corona free. Fortunately, unfortunately. So we are not interested in this because we have to find that person as corona or not. So we'll go with the corona cases. If in a corona negative cases, means corona free cases, still there are chances that he will be tested corona positive because that is the test, that is the actor. Otherwise, it is corona free. Okay, now what we want? We want this. We want this. Okay. Actual corona patient means if he is tested positive. Now just see from the kind of eye of, if corona test is a kind of active guy, from that point of view, just see the world. Now what is problem in corona patient? How many corona patient he thinks? Corona positive in corona cases and corona positive in free cases. All are corona positive from the test perspective. And then corona positive in corona cases. This is what we want. This is what we want. By this plus this. Okay. So this is what we want. This plus this. This is the total cases. And among them we want this as percentage. So when we do deep analysis, just we have to find the actor. If actor is decided, then goal is through. Okay. Now let's see what Mr. Bias thinks. Okay. As per Mr. Bias, this is corona positive. And another circle is corona test, not corona free. Now, if corona test is conducted, PA by T, If corona test is conducted, what is guaranteed that he is corona patient? Okay, PA by T. Now I have to know the PA, I have to know PT, then I have to know PT by A. If A is known, how many people are corona patient, then inside that, what is the test? Okay, so what we are trying to find is, typos are there everywhere. Okay, so what we are trying to find is, okay, so we are trying to find A by T, so that is PT and probability of A and probability of T if A has happened. Okay, now if I see T, then PA same as in taxi case. Okay, and so we can draw a tree. 0.1 is corona patient, 0.9 is corona free, and again inside corona free 0.9 into 1, okay, is corona patient, and inside the corona patient 0.1 into 0.7 is corona patient, and 0.1 into 0.3 is free. Okay, so we are not interested in this, and we are not interested in this. We are interested in this one, and we are interested in this one. So this is bias. Now PAPTA, so that is this one. PAPTA is this much, and PBTB is this much. Okay, so this is all about Bayes theorem. Okay, I mean, what we can kind of see is, everyone has its own eye. How you see the world. Okay. This is one eye of seeing the problem, and this is another eye of seeing the problem. But anyway, we'll go with whatever is the technology, whatever the technology is, and in future we'll see NLP, natural language processing, in machine learning. Okay, in future. And so what we achieved by now, that how we calculate the probability. First we understand the problem in depth, and we find the actor, Mr. Actor of the movie. Once actor is identified, then we create a complete space, and based upon the actor's eye, we find the sample space. Once sample space is decided, then we pick the item what we want, and then we divide what we want by total sample space seen by the actor. Okay, so Bayes theorem is same thing. So Bayes theorem is another way of what we describe. So if there are two orthogonal items, what we see, white and red exists in white and white exists in red, and if we know both probability, independent probability, and one conditional probability, what about the other conditional probability? Okay, so if this is the formula, then we deduce the other conditional probability is nothing but whatever the condition we are looking for, that condition, that probability, independent probability of the orthogonal one, and if orthogonal one exists, then what is the probability of be that condition what we are looking for. So that is the Bayes theorem, where Bayes theorem can be deduced through the tree structure. Okay, so from the real basic, the probability way, we saw that. So here, if a coin is tossed 3 times, then triple tossing, that is the actor that decides the actual picture, and in actual picture we find the whatever we want. And in a bag, if there are 2 green, 3 red and 2 blue balls, then actual actor is dual ball, because dual ball decides the scenario. and in the scenario we pick what we want and then we divide it. We calculate this by combination, not permutation. Okay, then we went to Bayes theorem. So if this is the case, like blue and red taxi and blue taxi is making hit and run case, as per the eyewitness, where eyewitness is only 80% true, in that cases, we find from the eyewitness, from the actor's eye, we find the sample space. So this is the sample space plus this is the sample space. So cross is gone and total sample space, what we see, and whatever we are looking for, we divide. Same thing what we did. Total sample space plus what we want. Okay, through Bayes theorem takes us into different world. So blue car is okay, blue taxi is okay, but witness I came into the picture, and then we say that I know PA, I know PW, witness PAW, then I have to find if W is there, then what is A. Okay, in another case, a city is 10% has 10% corona, 90% corona free. Okay, corona, if 70% corona positive case, if person has the corona, 90% corona negative, if doesn't have corona. So sample space is this much and this much. So both places, corona free places and corona case, both where corona patients are there. From the actor's side, corona test is the actor, from actor's side. If that is the case, then total sample item plus what we want. Now from the Bayes theorem, we see two orthogonals. Okay, so one orthogonal is, I think we drew it. Okay, we drew in other way. Okay, anyways, same case happens here also. So okay, so two orthogonal, one orthogonal and other orthogonal. Okay, so here also two orthogonal. One is test, that is actor, and another is whatever we see, corona patient. And same scenario arrives, test is down, and we have to find if test is conducted, then what is the scenario of the corona patient, being a corona patient. So finally we came to tree and we calculate the number of corona patient as per the test and what are the actual. Okay, so that is the Bayes theorem. Okay, so we'll see NLP later.